Good evening everyone. Welcome to the problem solving session of NPTEL course on ice engines and gas turbines. Today this is week 4 session. So today I have few questions related to the carburation and injection system for diesel engines. So this is the first question. What is the stoichiometric airfield ratio of petrol? Do anyone know what is the stoichiometric airfield ratio?
Sir, I think 15:1.
Yes, 15:1 is correct. Um, do you know what is stoichiometric airfield ratio? How do you define stoichiometric airfield ratio?
So the fuel air ratio that is chemically correct.
Yes. So if we have say methane as a fuel, and then we have oxygen, uh, where the oxygen will always have 3.73 parts of nitrogen because this constitutes air. Like one molecule of oxygen will be always comes with the 3.73 molecules of nitrogen, and this will gives to CO2 plus H2O plus nitrogen, and we will have, when we balance this, we will get some number here, say x. So now x, for we need x moles of air to combust 1 mole of fuel. So now so this is in molecular basis, molar basis. To convert this in mass basis, we have to multiply this with the molecular weight. So now we will have x into molecular weight of fuel divided by 1 into x into molecular weight of air divided by 1 into molecular weight of fuel will give the airfield ratio. So this airfield ratio is stoichiometric airfield ratio. This is generally noted as AFR ST. So then there is something called actual airfield ratio in engine terminology. So this is the actual mass of air by fuel at actual conditions, that is going to the engine. And again, related to this, we have something relating these two, we have something called phi. Can someone tell what is phi?
Equivalence ratio.
Yes, equivalence ratio. So equivalence ratio is defined as air fuel ratio stoichiometric divided by air fuel ratio actual. So when phi is equal to 1, that is both are AF or stoichiometric is equal to the actual one, so this we called as stoichiometric condition. When phi is greater than 1, that means for a given fuel, air fuel ratio stoichiometric is fixed, and if it is greater than 1, that means we have the denominator is less than the numerator. That means AFR stoichiometric is greater than AFR actual. So that means when compared to the stoichiometric airfield ratio, air for a given fuel, we are giving less air to the system, to the engine. So that means it is called rich condition. So that means it is rich in terms of fuels when compared to the stoichiometric condition. Similarly, phi less than 1 is the other way, and it is called lean condition. Now there is another term called lambda. Do anyone know what is lambda? Lambda is excess air ratio. This is directly, you can say lambda is 1 by 5. So this is other way of expressing the airfoil ratios. These are the terminology you will come across in many problems and even in research papers or real life. If you have any questions, you can ask me now, or I will move on to the next question. Okay. The venturi in the carburetor results in decrease of air velocity, increase of air velocity, decrease of fuel flow, or increase of manifold vacuum. Can anyone unmute and answer what is the answer for this? Okay, we have a venturi in the carburetor. Fuel is fed to this throat region from a float with fuel, and now this is the inlet condition, and we have the throat where the cross section area is lesser when compared to the inlet condition. So I would write A1 is greater than A2. So with the continuity equation, we will say for the same m dot, for a steady flow, we will say m dot at 1 and 2 are 0 or the same. Then we will have velocity at 1 or velocity at 2 is greater than velocity at 1. And if we want to talk in terms of pressure, we are using the Bernoulli's principle. We will say the kinetic energy has increased at the expense of pressure energy. So pressure at second state will be less than the pressure at the inlet condition. So here the answer is increase of air velocity. The choke is closed when the engine is accelerating, hot, cold, or idling.
Sir, I
Sir,
think
ideally.
accelerating.
Accelerating.
Sir, I think ideally.
Yes, sir.
No, actually choke is closed when the engine is cold, because this is like so we have a carburetor, and we have the throttle plate here, and we have a choke which will obstruct this passage further. So when the vehicle is cold, we need to enrich the mixture. So then we will close this block, this passage, so that very less air can leak through and go in, but there will be more fuel that can go through the venturi, and this will have rich mixture when we block the inlet passage. So this way we can ensure good starting combustion in an engine. So that is why we use choke during cold condition. So this choke, I think you cannot see in BS6 engine, but till BS4 engines where there was a carbureted engine, most of the two-wheelers with BS4 or previous vehicles used carburetor SI engines, and you can have seen a choke knob on the handlebar or somewhere in the near the engine. So that is used when the engine is not starting during the cold conditions. So when it is cold and you kick or you press the starter motor and it's not able to start for a long time, then you just block the choke, and then because of the rich mixture going into the cylinder, the first combustion will take place properly, and then you can release the choke. Lean air mixture is required during idling, starting, accelerating, or cruising. Okay,
Idling, sir.
idling. How do you say idling?
Sir, because while starting the engine, we don't have need lean mixture. We have to need rich mixture
Hmm. Yes.
while starting the engine. So then the starting option will not
Yeah.
correct,
Yeah.
and also I think accelerating also.
Yes.
And sir, yes, sir.
Okay. So based on other two, you chose idling. Okay. Yeah.
Yes.
Okay. Actually, the answer is cruising, because during idling the engine speed is very low. So during the engine speed is very low, and because of the low speed there will be more heat transfer, um, more high heat transfer during the low engine speed operation, because there is more time for the hot gases to pass the heat to the cylinder walls. So there will be high heat transfer during low speed operation, that is during idling. And during, so because of this there will be very unstable combustion, the combustion will not be very stable. So to make it stable we have to give rich mixture during idling. And only during cruising in the sense the load is like part load, 50% to 70% load of the engine, and cylinder wall temperature are very high, and the speed will be sufficiently good, so that there is no much of heat transfer as in the case of idling. And all conditions are favorable for a cruising to have a lean mixture. So during cruising we don't need to generate lot of power, but the engine hot temperatures are sufficient, the cylinder wall temperature are very good. So at this condition we can have a lean mixture. And during starting, as we just saw earlier, we need a rich mixture. So during idling we saw why we need a rich mixture. And during accelerating, the performance, the power generated by the engine has to be much higher than the regular cases, and because of this we will put more fuel and produce more energy out of the engine. So accelerating, during accelerating also we cannot have a lean air mixture. So the next question, the limits of air fuel ratio for SI engine are 8 bar 1 to 18 bar 1, 8 bar 1 to 50 bar 1, 25 bar 1 to 50 bar 1, 50 bar 1 to 100 bar 1. I think we just saw the air fuel ratio for stoichiometric is approximately 15:1. So that means this option C is doesn't have this range 15:1. So it is 25 to 50, it doesn't fall in the range, and 50 to 100 also doesn't fall in the range. And we have only these two options. And this is a property of fuel, so you cannot tell it by any calculation or something. There is something called flammability limits. So there is something called flammability limits, and there is a upper range, upper limit, and a lower limit. So this is a property for each fuel, and so what this upper limit says is, this is like for a rich mixture, assume the AFR can be as high as a 20 or 25, then a particular fuel can will be able to burn. And otherwise, so if it is more than air fuel ratio, if more than if the for a particular this one fuel, if the upper limit is 25, and if there is a fuel mixture of say 27:1, then it is too high for the fuel to get to take part into combustion, so it will not happen. So similarly, there is a lower limit, lean limit. Assume the air fuel ratio is 15, and then we have a lean limit of say 8:1, and then if you have fuel which is I think rich should be 8:1, right? So here this is air fuel ratio. So fuel is 1 and 8 is air, so that means this is rich in air. So 8:1, and if it is say if it is goes to 7:1, then it cannot burn. It will have a limit. And similarly for lean limit, there could be a limit of say 18, as in the case of gasoline. If it goes more than 18, assume we have a air fuel ratio in some mixture of 19:1, it cannot participate in combustion and have a stable combustion. So these are just properties of the fuels. And so for gasoline, it is in this range, 8:1 to 18:1. The hydrogen is considered as a new generation fuel, and it has a lean limit of say 5% to I'm not exactly sure, but it is somewhere in this range, 5% to 95%. So that means even with 5:1 of 100:1, yeah, for AFR 100:5, sorry, so that is 20:1. For AFR of 20:1, and so this is 95:1, that is 20:19. With this wide range, it can participate in combustion for hydrogen. So even if there is a small leak when you take a gas tank, hydrogen tank, and there is a small leak outside, generally what happens with the LPG tank is, if there is a leak here, somewhere here there is no fuel, right? Fuel is 0. I would write fuel air ratio is 0, and here fuel air ratio is infinite. So somewhere in between these two, there will be a small band which will have the limit of say this 8:1 to 18:1. So only this small region can participate in combustion, and that will not be much far from the LPG cylinder that I have mentioned. But in case of hydrogen, the limit is very vast. So as I said, 5% to 95%, and somewhere here it is 0, and here it is 100%, and here it is 0% air. So in the wide range it can participate in combustion. So any small leak of hydrogen can cause explosion. So that is a major challenge is using hydrogen as fuel. So next question, in SI engine for maximum power, the relative air fuel ratio is this. You could have seen a plot like this. Power to air fuel ratio, which is relative air fuel ratio. So one is stoichiometric, and say 1.2 is richer. Somewhere it peaks here, and then somewhere around 1.2 the power is maximum, and then it drops even if you go further richer or leaner to 1.2. So for SI engine, maximum power is obtained when the relative air fuel air ratio is 1.2. For maximum thermal efficiency, the fuel air mixture in SI engine should be so for this it is lean, because when we go richer, the gamma value is 1.45 here, right, and the Otto cycle efficiency is 1 minus 1 by R power compression ratio power gamma minus 1, and as gamma increases, that means efficiency increases. When gamma decreases, efficiency decreases. When you have fuel mixed to the air as a working fluid, this gamma value changes based on the fuel, and generally for gasoline kind of fuels, this gamma value drops when you have more fuel into the air. So that means gamma value drops for high fuel air ratio. So when you have rich mixture, based on gamma itself, the efficiency, the Otto cycle efficiency drops, and also because of the insufficient combustion or insufficient oxygen to complete the combustion, you will have unburnt hydrocarbon and other losses, so which will again reduce the thermal efficiency. So if you have CH4, let's give CO2 plus H2O. To balance this, you would have this and this. So this is stoichiometric condition. In actual, if you have a rich mixture, assume it is 1.5. So you'll have something like this. So when here you had 1:2, here you have 2:3, which means it is deficient of air. So that means then you will not have full proper air for combusting the carbon and convert to carbon dioxide. So there will be some carbon monoxide forms. So this means we have lost the potential of converting the carbon monoxide to carbon dioxide and gain more energy out of it, and because of this also we will have some drop in efficiency. During starting petrol engines require stoichiometric mixture, lean mixture, rich mixture, any air fuel ratio is alright. I think
Rich mixture, sir.
Yeah, sure. This I think I have explained in the previous questions where we saw why choke is needed or what choke does. So during starting we will have unstable combustion, and to make it stable we put more fuel. For petrol engines, the method of governing is hit and miss governing, quality governing, quantity governing, none of the above. Okay, the answer is quantity governing, because using a carburetor we have we meter the fuel based on the throttle opening and air velocity, air flow rate. So we meter the mass flow rate of the fuel directly using a carburetor. So this is quantity governing. And hit and miss governing comes for diesel engine, and this is not that all diesel engines have this. Few governor works on this principle. Economics.
Sir, please explain again. Sir, please.
Yeah.
Sir, please explain again this.
Yeah. So when we have a carbureted petrol engine, we have the assuming simple carburetor, we have this fuel float which meters the fuel in the venturi, and it get mixed and goes to the intake manifold, right? So here this m dot f is what we control, and this for the controlling this this is controlled based on the throttle plate and engine speed, right? Engine speed. So engine speed will decide the mass flow rate of the air, and also the throttle decides the pressure drop here. So here it will be atmosphere, and here it will be less than atmosphere, say vacuum, and then here further it will get reduced. So and all these parameters will decide the m dot f. So that is why we call this as quantity governing. I hope that is clear.
Yes, sir, that's clear.
Okay, economizer is used to provide enriched mixture during full throttle operation. I'm not sure if we have this is covered in the course, but you can refer in V Ganeshan textbook. There is a schematic which explains how the economizer works, and during full throttle operation it will enrich the mixture and make it rich, so that we will get more power out of the same engine. When throttle is suddenly opened, the mixture from the simple carburetor tends to become rich, lean, stoichiometric, not affected.
Rich.
Rich, how do you say that? Actually the mixture will become lean because when you open the throttle suddenly, the pressure here will gets higher, and there will be some lag for the fuel to come back to the throttle. So because of the inertia of the fuel and all, the air will moves faster than the fuel, and because of which we will get a lean mixture. So there will be less mass of fuel during when you open the throttle suddenly when compared to the steady state value. Choke is in an automotive meant for supplying. So this we have seen earlier. It is rich mixture. Choke, I have explained earlier that it will block the passage of the air, so that more fuel alone will go into the engine for better combustion, and this will ensure that engine starts even if during cold conditions. So modern carburetors provide the correct quantity of air fuel mixture during starting, idling, cruising, all conditions. So this is during all conditions. So there are different mechanisms to tackle individual conditions. So during cruising, the mixture has to become lean. During idling and starting, mixture should become rich. So when compared to a simple carburetor, there are different mechanisms to address these issues, and that is how we get a correct fuel air quantity for all the conditions. A simple carburetor supplies rich mixture during
Starting, sir.
So cruising.
no, actually during yes, during cruising it will become rich. During starting we need a separate component called choke to make it richer, and as such the simple carburetor cannot do that. And you can see from the derivation of this flow rate that when you have as you open the throttle plate, when compared to the closed condition, that is idling, so throttle closed means idling, this will be some fuel air ratio, and when you open partly, that means during cruising, and during this the fuel air ratio will become higher when compared to the closed throttle. I think this will come based on the derivations. I think someone is not muted. You can unmute only when you have to answer. So if you have any questions, I can answer now, or I can go to this problem.
So why is rich mixture needed while the vehicle is idling? Because there's no load on the tires, no load on the engine. Then why?
Yes, so as I explained earlier, yeah, during idling the engine speed is low, and because of this there will be a very high heat transfer. Okay, and also the engine wall temperature will be low. Wall temperature will be low, and because of this there will be very unstable combustion.
Okay, sir.
Yeah, so to make the combustion stabler, we will put more fuel, and rich mixture will be always stable when compared to lean mixtures.
Okay, sir. Okay.
Okay, so now we have a closed type injector, has a nozzle orifice of diameter 0.949 mm, and the maximum cross sectional area of the passage between the needle cone and the seat is 1.75 mm square. The discharge coefficient of the orifice is 0.85, and for the passage is 0.8. The injection pressure is 175 bar, and the average pressure of the charge during injection is 25 bar. When the needle 25 bar when the needle cone is fully lifted up, calculate the volume rate of flow per second of fuel through the injector and the velocity of the jet at that instant. density of fuel is 850 kg per meter cube. So this is about a diesel injector, mechanical injector, where the nozzle orifice diameter is given, and there is a maximum cross section between the passage between the needle cone and the seat is given as 1.75, and the discharge coefficient for the orifice is 0.85 and passage is given. So that means we can draw the system. There is some injection pressure, so injection pressure at 175 bar is there, and then this is connected to the seat area, and this will have some pressure P, and this is connected by the cross section area 1.75 mm square. I would say this is A1, and this coefficient is given, coefficient of discharge is given for the passages CD1 is 0.8, and then this is connected to the cylinder at pressure 25 bar, and there is an obstruction here or an orifice here, and this orifice diameter is 0.949 mm, and CD of this orifice is 0.85, and rho is given as 850 kilogram per meter cube. So now you know, based on the orifice equation, we have velocity across a orifice is 2 delta P by rho under root, and we know for continuity flow rate Q is A into V we know that the flow rate across all this is constant. So if it is Q here, then it has to be Q here on the next orifice also, because for steady flow there is, we consider there is no accumulation of mass in the individual system, and Q is same, so we can write Q1 as A1 to delta P. So here delta P is between injection pressure of I will write P injection minus seat area pressure. I would write P divided by rho. Rho is given as 850. Similarly, Q2 is pi by 4 d2 square, because only the diameter is given, and for the delta P we have and we have CD here, right? So here we have CD1 and here we have CD2, and then we have for the delta P we have the pressure difference between across the orifice, which is seat area pressure minus cylinder pressure. I note it down as PC. So now we have two equations where Q1 is equal to Q2, right? Q1 is equal to Q2. That means CD1 A1 2 P injection minus P divided by rho is equal to CD2 pi by 4 D2 square 2 into P minus 25 bar. Okay, I'll write it PC by rho. So this equation holds good. Now with this equation, only P is the unknown. So solving this, we will get the pressure at the seat area, and then applying it to any of the equation 1 or 2, we can calculate the flow rate, and that is what we are asked to do. And the velocity of the jet at that instant. So velocity of the jet is the velocity at orifice. Okay, so here CD1 is 0.8 and area is 1.75. I can have area in terms of mm, so because this also will be in mm, this also will be in mm, so I can have that. And within the root, this should be, pressure should be in SI units. And we have, okay, this 2 into P injection is 175 minus P is unknown divided by density is 850 equal to CD2 is 0.85 into pi by 4 D2 square, D is 0.949 whole square 2 into P minus cylinder pressure is 25 bar. So can someone parallelly solve this and find the value of P? Someone found it? I have got 151 bar. Can someone confirm if you have also got the same?
Sir, we are not finished yet.
Yeah, okay.
Sir, I got 220 bars.
Okay. It cannot be more than the 175, right? So we have a injection pressure of 175 bar on the left side, then we have some seat area and then cylinder. Is someone else also trying? Do you have any problem in understanding this? Okay, I think you will be able to solve this later. Now, assuming we have got the pressure at as 151.64 bar, then to find the flow rate, we can make use of any one of the equation 1 or 2. Then I am using equation 1, then I have CD1 A1 2 into P injection minus P divided by rho under root. So this is 0.8 into 1.75, 2 into 175 minus 151.64 divided by density, which is 850. So here it's better to have SI units everywhere. So this to convert the bar into SI units, we have 1 bar equal to 10 power 5 Newton per meter square, and this is 1.75 is in mm square, so then we will have into 10 power minus 6. Has someone got the answer for this? Okay, so the flow rate is 1.038 into 10 power minus 4 meter cube per second. And now you can calculate the jet velocity. So to calculate the jet velocity, we use V2 as 2 delta P, which is P minus P cylinder divided by rho, and this is 2 into 151.64 minus cylinder pressure is 25. To convert the bar to pascals, I have 10 power 5 divided by density. Can someone solve this?
One 172.61.
172.60. Is everyone getting the same value?
Yes, sir.
Okay, yeah, I also got it. So we have got the volume flow rate to the injector and also volume of jet at that instant. Now, okay, before moving on to the next problem, if you have any questions in this problem, I can clear now. Okay, moving on. We have a 6-cylinder diesel engine which produces 100 kilowatt at 1500 rpm. The specific fuel consumption of engine is 0.3 gram per kilowatt hour. Each cylinder has a separate fuel pump, injector and pipeline. At the beginning of effective plunger stroke of one fuel pump, the fuel in the pump barrel is 44 cc. Fuel inside the injector is 2 cc and fuel in the pipeline is 3 cc. If the average injection pressure is 300 bar and average pressure of change during the injection is 40 bar, average pressure of charge during the injection is 40 bar, calculate the displacement volume of one plunger per cycle and power lost in pumping fuel to the engine for all cylinders. Specific gravity of fuel is 0.9 and the fuel entering the pump barrel at 1 bar. Coefficient of compressibility of fuel may be taken as 80 into 10 power minus 6 per bar. So you would have seen this fuel pump. So there will be an inlet and outlet. So this goes to the injector, and this is a fuel inlet which is at 1 bar, and at outlet we have 300 bar pressure. And in the in cylinder we have charge pressure as so if it is injecting from here, this charge pressure is 40 bar. first we can calculate the fuel flow rate of the engine. So we have power as 100 kilowatt and speed is 1500 rpm and PSFC is 0.3 kilogram per kilowatt hour. So that means energy, brake energy is power into speed, power by speed. So here power is 100 into 10 power 3 watts or joules per second, and we have speed here 1500. Actually this is cycles per second. So we have 1500 revolutions per minute. That means we will have divided by 60 times revolutions per second. And since generally it will be a 4-cylinder engine, here it is not given, but still we can assume it as a 4-cylinder engine, and that means it will have one power stroke for every 2 revolutions, right? Then number of cycles per second. To get the number of cycles per second, we have to divide the RPM by 2. So this way we will have cycles per second in the denominator and joules per second in the numerator. Then this will cancel out and we will get energy for in terms of joules per cycle. So brake energy per cycle this is 8000 joules, and we have a 6-cylinder engine, so that means brake energy per cycle per cylinder is 8000 by 6, so that is 1333.3 joules. And we have told that the fuel consumption is 0.3 kilogram for every kilowatt hour. So we can we have this brake energy in terms of joules. So if we have the fuel consumption in terms of kg per joule, then we can directly get the kg of fuel that has to be supplied for every cycle, right? So to convert that, we will see what is 1 kilowatt hour in terms of joules. So this 1 kilowatt hour is 1 into 10 power 3 watts, that is joules per second, into hour. Hour is 3600 seconds. So 1 kilowatt hour will become 3600 into 10 power 3 joules per second, and second will get cancelled and we will have only joules. So essentially 1 kilowatt hour is equal to 3.6 into 10 power 6 joules. That means to calculate the fuel quantity, we have 0.3 kilogram per kilowatt hour. That means we need 0.3 kg fuel for 3.6 into 10 power 6 joules. But for every cycle we would get only 1333.3 joules. So for 1333.3 joules of brake energy, how much of kg we need, right? So that is 0.3 divided by 3.6 into 10 power 6 into 1333.3. So that is 1.111 into 10 power minus 4 kg. For one engine cycle, this is a fuel requirement, and we have given the specific gravity of the fuel is given, so that means density is specific gravity into 1000, which is 900 kilogram per meter cube. Now we can calculate the volume of fuel. Volume of fuel for every cycle is mass divided by density, right? So it is 1.111 into 10 power minus 4 divided by 900. So we have 1.234 into 10 power minus 7 meter cube. I hope you are able to follow the problem. If not, you can ask anytime. Now we will convert this into cc, because we were given the pump barrel, fuel in pump barrel is 4 cc, fuel inside the injector is 2 cc, and the pipeline is 3 cc. So it's better to have all the fuel volume in cc. So we have 1.234 into 10 power minus 7 meter cube will become 10 power 3 meters. So 1 meter I can write it as 10 power 3 mm, and then I would have this expression. Then it becomes 1.234 into 10 power minus 7 into 10 power 9. Okay, I actually need in cc, so I should write in terms of centimeters. I would have 10 power 2 centimeters. Then I would have 10 power 6 cc, centimeter cube will become cc. Now we will have 0.1234 cc. This is the volume of fuel that is required by the engine for every cycle. Now the total volume is volume, you have to add all this volume, fuel volume in the pump barrel, volume inside the injector and the pipeline. So that is 4 plus 2 plus 3. Plus the I think volume inside the fuel barrel is already considered, so this need not be added. So we will have this as 8 plus 11 cc. This is 9 cc. Now during compression, the pressure changes from 1 bar to 300 bar, and we can calculate the delta volume for this condition. So for delta volume, we know from compressibility K is delta V by V divided by delta P. No, sorry. Yes, here it is given, the compressibility is given per bar, so then we have delta V by V divided by delta P. So for every bar we are given the compressibility. So with this we will have here as 18 to 10 power minus 6 equal to delta V by total volume, which is 9 cc, divided by the delta pressure, and delta pressure is 300 bar minus 1, because at the plunger it is compressed, it is getting to compressed till 300 bar from 1 bar. So now we will know the delta volume. So delta volume is 0.2153 cc. So during injection, the plunger is reducing the volume because of compressibility, and when it gets pressurized, the volume is displaced by this much. Okay. So now we know to find the energy spent for compression or fuel compression work. Is P2 minus P1 into delta V. So we would have Newton per meter square into meter cube, then we will have Newton meter, which is joules. So P2 is 300 bar minus 1 bar. Converting this to SI units, we have into 10 power 5, and delta V is 0.2153 into, to convert the cc to meter cube, we would have 10 power 6. So this is the work. Sorry, this is 10 power minus 6, and that is 6.44 joules. So this is the work done by the injector to compress the liquid, compress the fluid. Now we were asked to find the displacement volume. So displacement volume is the one we have calculated here, delta V. So the plunger, the pump plunger has to move by only 0.215 mm for compressing the fuel and delivering the fuel. And next is to calculate the power lost in pumping fuel to the engine for all the 6 cylinders. So we have calculated the energy loss per cylinder and in terms of energy. So this we have to convert to power for all the 6 cylinders. So for 6 cylinders, we will have this as 6 into 6.44 30. So that is 38.64 joules per cycle for all the 6 cylinders. And similarly we have 1000, we need to know how many cycles per second we have. So that is by 1500 by 60 would give me revolutions per second, and dividing it by 2 I will get cycles per second, because for every 2 revolutions I have 1 cycle. So this is 12.5 cycles per second, and so power lost during compression is 38.64 divided by 12.5. So on the denominator I have joules per cycle, and denominator I have cycles per cycle. Oh sorry, I think then I have to multiply into 12.5. So that is 483 watts. Do you have any questions in the problem? Was this kind of problem or derivation dealt in the classes? I hope you are going through the weekly videos that is uploaded in the NPTEL portal or in the YouTube. Okay. Okay, I hope this problem is clear and we can move on to the next questions. So now I have few questions on injection system. Yeah. The first question is, fuel injector is used for gas engines, CI engines, SI engines, or none of the above?
CI engines.
Yes, CI engine is correct. And can someone say what is the advantage of having fuel injection instead of carburation system as in a SI engine? So when yeah. Someone want to answer? So in SI engine we have the carburation system. That means inside the cylinder so in the intake we have fuel, air plus fuel going in, and during compression you compress the fuel and air together. So during this time there is a chance that the and you have a spark plug and your intention is to combust the mixture only when the spark ignites, spark happens, right? But there can be some cases where if you compress more, then the temperature of the mixture can become very high and then it can start to combust on its own even before the spark ignites. So this case is very dangerous because it is inefficient because say the spark timing is given 5 degrees before TDC. We write it as 5 degrees before TDC, and if the self ignition occurs at around 15 degrees before TDC, then even when the piston is moving high, the combust gases will pressurize and it will push the piston down. So because of this we will lose a lot of useful energy, useful work, and this will lead to losses. And also the rate of pressure rise will be very high when during these conditions, and this is uh, explained by knocking. This term is called knocking. This phenomena is called knocking. And to avoid knocking, we need to have the compression ratio lower. And when we have a lower compression ratio, the Otto cycle or the standard air standard cycle efficiency drops down. So because of this, we are limited by the we have a limited efficiency. We cannot go beyond certain point. Now if you want to increase the efficiency further, you want to increase the compression ratio, but you have to avoid the problem of auto ignition, and this can be achieved by not sending the fuel and air mixture into the intake system, and you send only the air into the cylinder and then inject it instead of sparking. So you inject the diesel fuel when at around 5 degrees before TDC, like a spark timing, and then the combustion takes place, the gases expand, and then you get the useful work output from the piston. So in order to because of this kind of fuel injection, we are able to achieve more compression ratio, and we are able to achieve more air standard efficiency. So this is the main advantage of having a CA engine when compared to a carbureted SA engine. And nowadays we have something called GDI engine, which is gasoline direct injection, where we inject the gasoline fuel directly into the cylinder, and by this way we can also avoid the problem of knocking, which we have used to encounter in the conventional SI engine, and thereby we can also reduce the we can increase the compression ratio and increase the efficiency. So that way GDI engine is better when compared to the conventional SI engine. Advantages of air injection system is cheaper fuels can be used, MEP is high, fine automation and distribution of the fuel.
Option C, sir. Fine atomization and distribution of fuel.
Okay. This is one of the right answer. We can also use cheaper fuels because with the air injection system we don't have the plunger fuel pump with the plunger arrangement, where the lubricity and everything matters to avoid the leaking through this one, and also to have a proper lubrication. We need to have good quality fuels for to operate it in a mechanical fuel injection system. So when you have an air injection system, we can avoid this problem, and we can use any kind of fuel for burning. So we can also have cheaper fuels, and mean effective pressure can become high. So all the above is an option. Can anyone say why mean effective pressure is high? I hope you know what is MEP, right? MEP is mean effective pressure. I think this I have explained in my previous classes, so you can go through it and come back. So next question, commonly used injection system in automobile is air injection, solid injection, combination of AB, and none of them.
Sir, what was the last question?
You mean the entire question, or the whole question is advantages of having a air injection system?
Okay, sir.
Yeah, the answer is all of the above. I want you to find what is MEP, mean effective pressure.
So solid injection
Yeah,
is the answer.
yeah. What is solid injection?
So fuel is injected separately.
Okay. In case of air injection?
It is separated with the, it means it is injected into the cylinder with the air. So
Okay. In case of air injection system, in order to pressurize the fuel, we use a high pressure air. So this can be from a air tank uh, or uh, or a compressor which is working along with the engine to pressurize, and then we put in the container with the fuel, and then from here we give to engine, right? So here the fuel is pressurized to say 200 bar or whatever using the pressurized air tank. So this is called air injection. This is not commonly used in automobiles because this is a very bulky system and cannot be used in a moving vehicle. Whereas solid injection means we will have the plunger. So here the fuel is pressurized by means of air. In case of solid injection system, we have this fuel pump where there will be the plunger which moves up and down and pressurize the fuel in this chamber, fuel chamber. So this here we are pressurizing the fuel by means of a solid. So that is why it is called solid injection. And this is very small when compared to the air injection system, and that is why it is used widely in automobiles. Fuel injection pressure in solid injection system is around okay. You can choose 200 to 250 bar as an answer, but generally so there are different injection systems for solid category. We have mechanical injection system, and we have CRDI, common rail direct injection, and there were some different injection systems like unit injection systems in between, which came between the mechanical and the CRDA. In case of mechanical injection system, there is something called nozzle opening pressure. So nozzle opening pressure, so there will be a pump which will deliver high pressure to the injector, and this is put in the engine, right? And this is injector. So the pump pressurizes the fuel, and as the plunger moves, the pressure keeps on increasing in the line and the fuel inside the injector and the pump, and at certain pressure the nozzle in the injector starts opening against the spring action. So there will be a spring which is holding the needle in the closed position, and this fuel pressure will assist in opening the nozzle, or it exerts an upward force for the nozzle, and it overcomes the spring force, and at certain pressure of the fuel it can overcome the spring force, and it can open the needle can open. So this pressure at which the needle can lift and open the nozzle is called nozzle opening pressure. So this is typically 200 to 250 bar, and after it is open, the plunger in the pump can move further and increases fuel pressure further. So that is generally called as fuel injection pressure. I think it is the same here. So It is generally called as injection pressure, and it can go up to, say, at low loads it will be 300 bar, and so 600 bar at part load, and can go up to 900 bar, or in some cases it can go up to 1000 bar maximum. This is in case of a mechanical injection system. Whereas in case of a common rail system, in the very preliminary stage in around 1990s, we had a common rail system which whose pressure capability is of around 100,000 bar, and very recently it has become like some 5 years back it was 2000 bar, and currently the common rail systems can go up to 3000 bar, and this pressure is increased continuously, so that you get a good automation and a better combustion inside the cylinder. Any questions? Okay. Fuel filters do not use generally paper, because paper has a tendency of getting ruptured and getting into the fuel stream, and this paper particles will clog the fine injection holes. So the injector will have very fine holes. As we saw in one of the problems, the orifice diameter was 0.949 mm. So this is a case of a old injectors. Nowadays, as I said, for a CRDA injector with 3000 bar pressure capability, the needle diameter, orifice diameter will be around 0.15 or 0.12 mm. So that means 120 to 150 micrometer. So this is very fine hole, and any small particle from the paper can clog this. Fuel is injected in a 4-stroke CI engine at the end of suction stroke, at the end of expansion stroke, at the end of compression stroke, or at the end of exhaust stroke.
C at the end
At the end of compression stroke.
Yes, that is right. So you have the pressure volume curve. I start the cycle with from the TDC. During suction, we suck the gas into the cylinder. So it moves down, and the volume increases when the piston moves down, but the pressure decreases because there is a small opening for the air to enter in, and through the restriction it is sucking the air. Because of that, the pressure inside the cylinder will be slightly less than the atmospheric pressure. And then after the suction process is over, we compress, and pressure during compression the pressure increases and reaches a maximum value. At this point we will inject the fuel with which the combustion occurs, and then the pressure rises further, and then it expands with a higher pressure when compared to the compression curve. And then during exhaust stroke, the exhaust valve is open, the gases move out, but the pressure inside the cylinder will be little higher than the atmospheric pressure, which can push the gases out. Injection system in which the pump and the injector nozzle is combined in one housing is known as injection system in which the pump and the injector nozzle is combined in one housing. So this system is called as common rail system, distributor system, unit injector system, individual pump and nozzle system.
C also, sir.
Sorry?
C.
C.
Okay.
Yeah, unit injector. Right. In case of a unit injector, for every cylinder there will be a cam driven lobe, and there will be a plunger which is in contact with the cam and moves vertically for this to compress the fuel, and then you have the injection system. So this is actually this will be inverted. So this is injector, cam, plunger. So all these are put in the same casing, and then the injector injects the fuel into the cylinder. This is called a unit injection system. What other injection system is familiar to you? The basic injection system is the individual pump and nozzle system, where for every engine cylinder there will be a pump which is attached to the crankshaft, and this pumps the fuel and injects the fuel into the cylinder. So there will be each pump for every cylinder. So if there are 6 cylinders, there will be 6 different pumps. And in case of a distribution system, there will be one distributor unit, and there will be for a 6-cylinder engine there will be 6 fuel lines coming out, and in the engine block each one go to each cylinder and will be connected to different injectors. So, and this distributor in turn will be connected to the engine crankshaft. Engine crankshaft or engine camshaft. And the common rail is a modern technology. So here you have a common pump, and this is electrically actuated. So based on the electrical pulses it will pump more fuel or less fuel, and then there is a common rail which will store the high pressure fuel, and there are different say for a 3-cylinder engine, each injector is connected to each line from a rail. So the rail pressure will be maintained constant using sensors and actuators to around say 1000 bar or all the way up to say 2000 bar, and this rail pressure will be there all the time throughout the engine cycle, and the pressure will not drop significantly. And when it has to inject, the ECU or the engine control unit sends commands to each injector individually, and then based on the electrical command it will inject. So there will be some solenoid which opens the nozzle, opens the needle, and it can inject. And similarly pump is also controlled by the ECU. So this is called as common rail injection system. They call it common rail direct injection. So that is common rail system. Only in this case, throughout the engine cycle, you will see high pressure maintained at the rail. But in case of injection, the individual pump system, you will have pumping event. After the pumping is done, it will go back to a lower pressure, and only when the next injection has to happen, the plunger moves and pressurized fuel. And same with the distributor. Only thing, instead of having different pumps for different cylinders, it all goes into a single unit called distributor unit. And in case of a unit injection system, there are different injection plus pump system, but this pump and injection system comes in a single unit. And again, the line is pressurized only when the injection has to happen. So other times the line pressure is very low compared to the injection pressure. Only in common rail system we maintain high pressure throughout the engine cycle. Any questions with this systems?
No, sir.
The most accurate gasoline injection system is direct injection, port injection, throttle body injection, or manifold injection.
D, sir.
P, port
So
injection.
no,
Sorry?
so no any question.
Sorry, you have a question.
So she said no doubts.
Oh, okay, fine. Okay, so the most accurate gasoline injection system is port injection when compared to throttle body or manifold injection system. So in case of manifold injection, so assume we have a 4-cylinder engine. There will be 4 ports for the intake manifold, and then there will be a common manifold, and then from here it goes to the filter. In case of port injection, each injector is placed at the port of the engine, so that means it can it can inject the fuel, and in the next cycle the engine sucks in the fuel and use it for the combustion. In case of throttle body injection, so there are different systems, like some engines will have throttle body here as a common throttle body for all the engines, for all the cylinders, and if you inject here, then it can happen that the most of the fuel or the air goes to the least path and not to the farther cylinder. So because of this, there will be continuous degradation of the cylinders which are near to the throttle body, and which are far to the throttle body will always deliver will get low fuel and combust less and delivers less power, and also deteriorates less. In case of manifold injection, you inject into the manifold directly, and again here the same problem arises. So when compared to all the systems, only in a port injection system you have precise control of the injection, and it can deliver the fuel across all the cylinders evenly. Advantages of fuel injection in SA engine. So low initial cost, low maintenance requirements, increased volumetric efficiency.
C, sir.
C.
हाँ जी sir.
Sorry.
Yes sir, the answer will be C.
Okay. Can someone explain why it is C? Okay. In case of a carbureted SI engine, we have, or not only carbureted, but even for a port fuel injected engine, we have a throttle body here, which restricts the air coming in, and fuel is fed through here, or fuel is injected here, right? So when you have a pre-mixed, so in this case the fuel is mixed before the combustion properly, unlike the diesel engine, right? So this is called pre-mixed combustion. So in case of a premixed combustion, as we saw earlier, there is something called flammability limits, and there is a upper flammability limit and lower flammability limit. So that means I can say there is a rich limit and lean limit. Within this range only, the combustion can take place at a steady phase, and combustion can take place steadily, or also the fuel can participate into the combustion. If it is outside of this range, the fuel can not even participate in the combustion. So to ensure that, so because of this, we should always maintain the air fuel ratio of the engine to some limit. So as we saw earlier, it is 8:1 to 18:1 for gasoline engine. And now assume we want to have engine, say it is a 5 kilowatt engine, but currently I need to generate only 0.5 kilowatt. Assume we are in a street, the vehicle is going on a street and in a city traffic where the speed is very low and there is no much acceleration, so the power requirement is very low, and for this low power output, I can just reduce the fuel input, but then I will fall outside of the lean limit. So that means if I don't have the throttle, then I will be, if there is no throttle, then the air will be flowing same as all the cycles, and if I reduce the fuel, just reduce the fuel alone, then I will have a limit of 18:1, beyond which I cannot reduce the fuel and have a stable combustion. So what I have to do is I should reduce the air also in proportion to the fuel to have a stable combustion. To achieve this only, we have a throttle plate, and by changing the throttle position or by restricting the passage in the cylinder intake flow, we are able to control the power output of the SI engine. So because of this, during suction stroke, as we saw in the PV diagram, when during intake stroke, the piston moves from the TDC to BDC, and during this the pressure reduces, right? And if we have the throttle restricting this one, restricting the flow, we will have further reduction in the pressure. And because of and during expansion, during exhaust stroke, we will have a slightly higher pressure than the atmospheric pressure, and this area under this in this loop is called pumping loss. So that means we are spending some energy to take the air inside. Because of the restricted flow, we have to spend more energy when there is a restriction when compared to no restriction, and because of this we encounter in some loss called pumping loss, and this loss is very high when the power requirement is low. As power requirement is low, we need to give in less fuel and we have to restrict the air passage, and we restrict the air passage, we end up in having pumping loss. So to avoid this, we can have we can avoid having premixed combustion and have something called diffusion combustion. Or partially premixed combustion. So diffusion combustion is mainly for a diesel engine. In case of GDI engine can operate both in diffusion and partial premix mode. So when we have fuel directly injected into the cylinder and we have a spark plug nearby, so assume we have a injector injecting fuel and we have a spark plug, right? Now the entire combustion chamber is like this, but we have fuel across only this region, and we are outside of this region it is only air, so there is no fuel. So instead of restricting the air passage, like having a throttle and maintaining the air-fuel ratio, we can also stratify the charge and mix the fuel for only a small region of combustion chamber, and then we can achieve stable combustion even in the part load condition. So because of this we will avoid pumping loss and we will avoid throttling effects, and this will also in turn increase the volumetric efficiency. So when you remove the throttle from the engine, you will have more volume, and also even at part load we will have the same volumetric efficiency as in the wide open throttle conditions. Do you have any questions?
Sir, could you repeat it?
No, sir.
Okay, I think someone else had a question.
Could you repeat it once, sir? Thoroughly.
Which part you
In
didn't
short,
understand?
Sir, I just sir, I just want you to repeat it in a summarized way, sir.
Okay, I will just summarize. In case of a premix combustion, as in the case of carbureted SI engine, we have to follow the flammability limits for stable combustion. So the flammability limit of gasoline is the air-fuel ratio should not go less than 8:1 and not more than 18:1. So this is a rich limit, 8:1, and 18:1 is a lean limit, right? We are putting more air, which is 18:1. We are putting very less air compared to the stoichiometric, and that is rich limit. So if you go beyond this limit, if you have a mixture of 7:1 or 19:1, combustion will not take place. This is just a property of the fuel. Okay. So now you have a very large capacity engine, say 5 kilowatt engine, but currently you want to produce only 0.5 kilowatt of power. Then that means you have to essentially put less fuel energy into the system, but just by reducing the fuel input you cannot achieve a stable combustion. You have to decrease the air also proportionally. So that is why we have a throttle body in the SI engine, where we reduce the mass flow rate of air inside and also reduce the fuel flow rate of the fuel flow rate inside. Thereby we will be within the flammability limit of the combustion, but we will supply less fuel, which will produce less power output, which is our desired state. So when you have a throttle and restrict the passage, you will end up in having pumping loss, because you are sucking the air inside with some restriction in the intake path. So because of this you have a pumping loss, and you will also have low volumetric efficiency. And when you have a direct injection, fuel injection, where you inject the fuel directly into the cylinder, you can have a stratified combustion like this, where you have a small space of the combustion chamber with the air fuel mixture, and outside of this can be pure air. So this is whereas in case of premix combustion you have to fill all the space with the fuel and air, and that has to be within the flammability limit. Now only this region has to be within the flammability limit, and this you can have less fuel when compared to the premixed combustion phase. So because of this, you need not have a throttle body for a direct injection SI engine. So you will have benefits of avoiding pumping loss, and you will have high volumetric efficiency. I hope I have
Yes,
made
sir.
it
Yeah.
clear. Yeah.
Yes, sir.
Any other questions? You people are which year you are doing? I hope you are doing mechanical engineering bachelor's, right? Most of you.
Yes, yes.
Yes, sir.
Which year you are in?
Yes, sir.
Third year.
Third year.
The third year.
Okay.
Fourth year, sir.
Okay.
Sir, I am third year.
Third year. Okay. Okay. I think you would have, if you are in third year, you would have already got this course in your UG, right? Or you don't have till third year.
We are pursuing this subject via NPTEL, sir, rather in our college, sir. The college
Sorry.
has the college has issued this subject mandatorily from NPTEL, sir. Rather
Oh.
giving rather giving exam in the college, sir.
Oh. Okay. Okay. May I know which institute you are?
Subhati Institute of Technology, situated in Meerut,
Meerut. Okay.
yes,
Meerut.
sir, Uttar Pradesh.
Okay. Okay. So if you have any questions, you can feel through us. Generally, people do NPTEL course as a as additional courses to what they are doing in the university, right? So then this becomes more responsible for NPTEL and us. So similarly, you have some other courses also, like IC engines to be taken from NPTEL, or it is only one course?
Minimum one.
Minimum one.
Yes, sir.
Okay.
We can choose all of the subjects too, but we have chosen this one subject
Oh,
for the
okay.
rest of the time. Then we'll see in the next semester whether to choose more than one or
Oh,
just
okay.
one.
Okay. So you have to write the exam, and then that only will be considered in your grading sheet, right?
Yes, sir. We perform examination at the 30th April, right?
Hmm.
And after that, the NPTEL certification. If we got NPTEL certification, if we got passed, then the NPTEL shares our mark sheet to our college, and then
Oh,
college
okay.
will
So they directly share to your college. So they have a
yeah,
tie-up.
college, yes, sir, college, like we have we have ticked out in the that what to say, while filling form, na, sir,
Yes, yes.
that we have ticked to share our mark sheet to our college as well, na.
Oh,
That,
okay, okay, okay.
so after having examination and after getting result, the
Hmm.
mark sheet of IC engine will be given from that certificate, sir.
Okay, okay. So how many of you from your class are in this course? Like everyone or few?
Right now, I am the only one, sir.
Okay. But how many would have taken the course?
There are like 17 to 18 students, sir,
Okay,
taking
okay,
different courses, sir.
okay, okay. And what about other people? You also have a mandatory university course and you are joining here, or it's just out of your own interest?
No, sir. It's not mandatory in our college.
Okay,
It's just for extra credit.
okay, okay. Okay, and you can take this credit and use it in your grade sheet, is it?
No, sir. This is just
Okay,
apart from the syllabus.
okay, okay, fine.
However, we can uh, get this credit of
Hmm.
this subject.
Okay, okay.
Sir, may I know more about air injection and solid injection, sir?
Yes. More in the sense, I will tell. Yeah. So in case of air injection, in order to pressurize the fuel, we use the compressed air. That can come from a air tank or from a compressor, right? And this compressed air is used to pressurize the fuel, and then this pressurized fuel tank is fed to the engine, and there is no pump involved, there is no fuel pump involved in case of a air injection system. In case of a solid injection system, you have uh, you have a plunger you have a pump with a plunger which pushes and pressurizes the fuel, and this pressured fuel will get to the injector and then it will get injected. So here in case of solid injection, the pressurization, the fuel is pressurized by using of a solid medium, solid plunger. So that is why it is called solid injection, and the other one is called air injection.
Sir, what is the difference between what do you mean run on ignition, sir?
What ignition?
What is run on ignition?
Run on ignition.
Yes, sir. What does it mean, sir?
You mean to say run on ignition?
Yes, sir.
Where did you see this? I am not aware
Somewhere
of
in
this.
assignment, sir.
Sorry?
Somewhere in assignment, sir.
Oh, assignment.
Yes,
Actually,
sir.
you should not discuss the assignment which are open to me, and I should not be supposed to tell answers for assignment questions which are.
I'm not asking the answer, no, sir.
Yeah,
I
yeah,
just
that is okay. But I am also not sure what run on ignition means. Can you tell me the question?
which of the following cannot be used by a hot spark plug? Ignition, post ignition, run on ignition, detonation. That's I'm getting confused between these two options. Run on
Mhm.
ignition or post ignition.
Mhm. Actually, I also am not sure what run on ignition means. I will I will look into it and I will get back to you in the next week.
It's very confusing, sir.
Sorry?
It's very confusing, sir.
Mhm.
Some of the questions are very confusing.
You have a book, right? They have suggested you some books, right?
Yes, sir, yes, sir. I have booked.
Okay. Maybe you can search in the book, you might get. I will also search in book only. I am not sure what run on ignition means.
Okay, sir.
Any other questions? Okay, then if there are no questions, we can meet in the next session. Thank you everyone for attending. I will close the session now. Thank you.
Thank you.
Thank you, sir.
Thank you, sir.
अस्सी वाली लेके